We have already discussed a few of the techniques like a brute force approach, divide and conquer technique, as well as decrease and conquer technique. So in addition to that, we'll be talking a few more problem solving techniques. Among them, in today's session, we'll be discussing in detail about your transfer and conquer technique. So here in this case, in the technique of transfer and conquer, so we have two major stages. So one is the transfer and another one is here conquer. So transfer in the sense, so we want to bring your problem into another problem instance. So it's something like this. You can see the pictorial representation over here. So this is your problem instance. So this problem instance should has to be brought into another instance. So which should be simple, or it should be of another representation, or it should be of another problem instance. So you can have any one among these three variations. So this transformation, we call it as a transfer stage. So once the problem has been transferred, it's the responsibility of us to solve that transfer instance. So that is why this particular problems are being called as transfer and conquer. So here also it has been mentioned over here, there are three major variations. One is, as I already mentioned, instance simplification, change of your representation, and third one is your problem reduction. So first we're going to consider your first variant of instance simplification. So here in this case, I want to take an example of checking element uniqueness in a given array. So there are some elements, n number of elements. So in these elements, so I'm supposed to check whether these array elements are unique or not. I mean to say that, so no two elements should be same here. If I go with your previous approach of brute force here, so this is what the procedure I used to adapt. The very first element I can consider as a key. It should be compared with all the remaining element in the given array. In this case, 10. It will be matched with all the elements, no match. Go to the next iteration. Consider the second element, 5. So 5 will be compared among the remaining elements that is present towards the right of it. Again, no match. But in the third iteration, if I consider your third element as the key element, so this element found at the last position. So obviously here in this case, it returns the value false. Here returns true in the sense if A has no equal elements, or else the false here. So here if I want to estimate the time complexity of that, so we need to have two for loop. Within the two for loop, we need to have a comparison statement comparing with all the elements of the given array. So obviously its worst case time efficiency will going to be theta n square. So we need to see that, so whether in this transfer and conquer technique, so whether this worst case efficiency will going to be reduced to a certain extent. So first let me go with your concept, and later on I can try with the algorithm. So here in this case, as I already mentioned, in the transfer and conquer technique, first the element should has to be transferred into a different instance, and that different instance should has to be solved. So the first phase I'm doing over here is sort the array. So in fact, we use the concept of pre-sorting here for many of the examples. So we adapt the concept of pre-sorting because we are already familiar with the concept of pre-sorting. That means the sorting technique. So we adapt this pre-sorting here. Sort the given array, whatever the element that has been given. So sort it I just consider the same old array elements, this 10, 5, 6, 12, 8 and 6. I sorted it and compared with the adjacent elements. 5 will be compared with 6. Just compare only with the adjacent element. This 5 should not be compared with 6 again. Suppose if this 5 equals to this value, it means that they are not unique. If there is a mismatch, then this element should be compared with the adjacent element that is located next to that. 6 will be compared with this. Obviously, it's equals. So in this case, we are supposed to return the value false. So here in this case, I'll go with a linear scan. For I is equal to 0 to n minus 2, do if a of 5, initially it is 0, this index equals to the next adjacent element. If they are equal, returns false. So I am supposed to be in a loop until I traverse all the elements. So here in this case, the condition should be n minus 2, because your index should not point to the till to the last position. It should be point to the last but one position. So it should be up to here. So this adjacent element will going to be n minus 1. That is I plus 1 here. So if it doesn't matches, so finally I'm supposed to return a true value here. If I want to estimate the efficiency of that, so this problem, as I already mentioned, that it is having two stages. One is the transformation and another one is a solution, that is conquer. T of n sort. So here there are a lot of sorting techniques. I think at this moment of time, you people have already learned a bubble sort, selection sort, insertion sort, pick sort, merge sort. Among them all sorting technique, your merge sort and quick sort will going to have a best time efficiency. Its time complexity will going to be n log n. And for this linear scan, so this comparison is happening only within this for loop. So its efficiency will going to be theta n, because this comparison will going to be happening n minus 1 times. So it is theta of n. As we know, with respect to the theorems of asymptotic notation, so when we have the summation, so we need to consider the maximum order of growth among these two functions. This is linear and this is n log n. So finally the resultant will going to be theta n log n, because this is having higher order of growth compared to this one. So even I can show this scenario. So in your what is this PPT also, let me show over there. Yeah, here it is. Understand the concept of transfer and conquer. The problem is given. We need to transfer that problem, and finally for this we need to find out the solution here. So transformation happens. So the three variations for transforming your problem: instant simplification, change of representation, and problem reduction. So there are a lot of examples which uses these applications of pre-sorting. So one among them is your determining the uniqueness in a given array. Just now we discussed. Input an element, first transformation, sort the input, and then trying to find out the solution for that. There are a lot of other examples, so which adapts the application of this sorting. Find if there is any repeated number, search, find the mode, frequency, median, etc., etc., etc. So in your syllabus, obviously we'll be concentrating on these three examples. So they have given this very good example on this PPT slide also. 15, 3, 4, minus 12, and 2. Initially is adapting the concept of brute force approach, where each element will be compared with the adjacent elements. Okay, you just have a look into it. 15 is the key element, and it will be compared with all the elements. 15 will be compared with 0, doesn't match. 15 will be compared with 4, then 12, and then 2. Okay, so it doesn't matches with any of the elements. So next I'll consider 3. So in fact it was not 0, it is 3 actually. So I'll consider 3 as a key element. It will be compared with the remaining element that is present in your given array, that is towards the right of it. It will be compared with 4, minus 12, as well as with 2. You can see this comparison. Yes, it doesn't match. Next, 4 will be considered. Again, it matches with the remaining 2 elements. It doesn't match here. Minus 12, the key element, comparing with 2, it doesn't match. So here in this case, the time efficiency will going to be theta, or worst case, obviously it will going to be big O of n square. So in the technique of transfer and conquer technique, so we are reducing that instance to a certain extent here. See here, you can see this tracing operation here. As a first phase, I need to order this element. That means I'm supposed to arrange this element in an order actually. So I'll prefer with an ascending order here. Minus 12, 2, 3, 4, and 50. It's been ordered here. Okay. Now, compare among the adjacent elements. That's it. Minus 12 should be compared with 2. 2 should be compared with 3. 3 should be compared with 4. 4 should be compared with 15. Just scan, a linear scan for the repeated numbers. If you make adjacent element comparison, if they are equal, then we can say that there is no, I mean to say that if they are equal, there is no uniqueness in a given array. You can see the comparison here. Minus 12 will be compared with 2. That's it. Next 2 will be compared with 3. Just one comparison. 3 will be compared with 4. And 4 will be compared with 50. Done. Okay. You can see the algorithm here. Sort the least. That's the transformation stage. Right? I want to determine whether the array elements are unique or not. First, sort the least and then do the linear scan. For I is equal to 0 to n minus 2, if a of phi is equivalent to a of I plus 1, just compare with the next neighboring element. That's it. If they are equal, return false. If I am returning the value false in the sense, so there is no unique element. If I complete through this scan, still if I do not find the 2 elements unique, so then I'm supposed to return the value true. If I return the value true in the sense, there is no existence of a, I mean to say that there is a unique element that exists in the given array. So this is what the complications is. That is the time efficiency, T sort, T scan. This is the first phase. This is the second phase. For T sort, there are lots of sorting algorithms. I think you're already familiar with. You can see over here, selection sort, bubble sort, insertion sort, right? Quick sort. And all these algorithms are yielding with the time complexity n square. I don't want to go with that. Quicksort and mergesort are yielding with the time complexity of n log n. I can prefer among these two any one algorithm. Let me go with your merge sort. So T sort will going to be having the time complexity of n log n if I'm using the algorithm merge sort. For scanning, it is big O of n. So finally, the time complexity, I can say that among these two, the maximum order of growth. The maximum order of growth is n log n. So obviously, to determine the uniqueness in the given array, So the time efficiency will going to be big O of n log n in the case of worst case. So this is one problem under the category of transfer and conquer technique. So where we adapted pre-sorting before we try to solve the problem. Okay. And I'll have another problem. I'll go in the order of your textbook materials. The same thing, pre-sorting. There are lots of applications you can solve by adopting this pre-sorting methodology. This we have done, checking element uniqueness in a given array. This is the given algorithm which I showed in your PPT also. And finally, the efficiency will going to be n log n. The second example. Again, this example will also take a pre-sorting method to perform a transformation of a given problem. I want to compute a mode. So obviously we are supposed to know what exactly the mode is. A mode is a value that occurs most often in a given list of numbers. Maximum number of times which number exists in your given number. So that will going to be your mode. So in this particular example, for each of the number, determine its frequency. Frequency in the sense how many times it exists in a given array. 5. So it is present 3 times. 7, it's 2. 1, it's 1. 6, it's 1. So maximum times the element that is occurred in this given array is your 5. It's occurring 3 times. So the mode value will going to be 5. If you go with a brute force approach, the same concept which you adapted in the previous example of determining the uniqueness in a given array, the same strategy we are supposed to use. This element will be compared with all the elements. Wherever it finds a match, we need to increment the count of that particular frequency. So in that way, we are supposed to determine the count of each individual element, right? So obviously here also the time complexity will going to be theta n square. Let's see at what extent we can reduce this time efficiency. So we have the algorithm here, pre-sort mode. So as a first stage, I'm supposed to sort your given array A, and always current run begins at position I. That means the index value will going to be 0. Highest frequency seen so far, as it's the initial iterations, we have not seen any frequencies. So the frequency value will going to be 0. So basically, mode value will tell us what's a mode value is. Mode frequency variable will going to tell us how many times this mode value occurred in your given array. So in that previous example, if I just look into this, here mode value will going to be 5 mode value, right? And its frequency will go to mode frequency will going to be 3 only after the end of the algorithm here. Okay, so initially it is 0, I is 0, mode frequency is also 0. While I less than or equal to n minus 1, I'm supposed to make a linear scan among your n number of array elements. Run length is equal to 1. When I consider a single element, so its run length will also be 1, right? This should keep on incrementing, and finally at the end I'll going to initialize that one to the mode frequency. Even a unique value will going to have the frequency of 1. Okay, so initially I consider that itself as a run value, and run length is equal to 1. I plus run length should not exceed this n minus 1, and a of I plus run length should be equal to run value. That means with adjacent element. can show it over here. 6. I is 0, the initialization, mode frequency is 0, run length is 1, run value is E of I. So here, this value will be compared with this adjacent element. If it doesn't match, I'm supposed to stop there, right? See here. This doesn't equals here. I'll come out. Run length. What's the run length value at this moment of time? It's 1. Greater than the mode frequency, initially, which I consider it as 0. It's greater. So mode frequency at this moment of time, it's your run length, that is 1, and mode value will going to be your run value, which I consider the very first element, where the very first element will going to be your 1. Getting my point? See here. So mode value will going to be 1 and mode frequency will be 1. And I will be incremented with respect to your run length. Be in this loop. Now I will going to be pointing to the second index element, 1. 1 less than or equal to n minus 1. Run length is equal to 1. Run value will going to be A of 1 now. This one. Okay. So this will be compared with its adjacent element. Here it happens. This condition is only for not exceeding your array size. This will going to make a comparison with the adjacent element. If it is equal, keep on incrementing the run length. So in this case, run length increments. Now it becomes 2. Then compare this with again with this element. Again the run length will going to be incremented by 1. Now it becomes 3. This condition becomes false when this compares with this. Okay. So we'll come out from here. If run length greater than mode frequency. So initial mode frequency is 1 for your index, for your element 1. So now run length is 3. It's greater. Update your run length and run value for this mode value as well as for mode frequency. Now the mode frequency will be 3 and mode value will going to be 5. And increment I by I plus run length. I is equal to I plus run length. I will be 1. 1 plus 3. It will point to the index 4 here. It will come to this. Because again, this won't compare with this, right? We come here. 6 will be compared with 7. No. So run length will be 1. Okay. So this one is not greater than the already existing mode frequency, which is 3. So this conditions doesn't hold good. This value will not be updated. I is equal to I plus run length. So it points to this. 7 and 7. Yes, they are equal. Run length will be incremented by 1. It becomes 2. But there is no adjacent element to this. We need to come out from this loop. Run length will going to be 2. Mode frequency, already existing mode frequency is 3. So mode frequency value will be not be updated because this condition doesn't hold good at this moment of time. Will come out. I is equal to I plus run length. Obviously, it will cross over your array limit. Will come out of this outer while loop and finally return the mode value, where the mode value will going to be 5. So here in this case also, this is a basic primitive operation, this comparison, but this has been kept within the 2 while loops. Obviously, here also it should be n square, but the thing is, in the innermost while loop, we are not going with all the elements. We are going with very few elements here. So obviously the time complexity will going to be less than your n square. Okay. And this first part, we are using this n log n, the merge sort, and this will going to be n square. The maximum we should consider. Obviously, this is the one, it will come into the picture, that is n square. But here in this case, so its efficiency will not be up to the maximum of n square. It will going to be less than n square. Obviously, we can say that from the previous approach, that is from brute force approach. So here we're going to be have certain reductions. Okay, so we can see some improvisation. And third problem, a searching problem where we are using your binary search. So as you've seen in your binary search, the prerequisite is first we need to sort your elements and then only we are supposed to perform a search operation. So for sorting n log n, again, I don't want to go with the concept of your binary search. And the second part, the searching. So it will take the time complexity of theta log n, the maximum among these two. That is theta n. Okay. So these are the three problems. So which comes under this particular category of pre-sorting of your transfer and form. Okay. So with this, I'll stop my